Our last application of the derivative is in regards to related rates of change. Basically, these are physical word problems. We're using calculus to solve some word problems. All right. What's ultimately going on is we're trying to come up with a real-world situation in which an object is changing over time. So for example, you head down to the local flower shop for Valentine's Day and you have them blow up a balloon, and as they're blowing up the spherical balloon, a bunch of things are changing about this balloon. Its volume is changing. The radius of the spherical balloon is changing, as is the diameter, and so is the surface area of the balloon. And there's a relationship between all three or four of those characteristics. We're looking to find that relationship, and then based off of given data, we can come up with specifically how fast the volume is changing at a particular time. Right. So that's ultimately what's going on here, is a real-world connection, and we're finding the connection between the derivative of variables of a particular geometric formula in most cases. It may not necessarily be a geometric formula, but in many cases it is. Okay. Now, the thing to keep in mind here is when we talk about the derivative is most of the time when we found the derivative so far, it has been in terms of x. In other words, dy dx. We're deriving with respect to x. With these word problems now, we're no longer deriving with respect to x. These objects are changing over time. So our variable is going to be time, or t. So when we derive, we're going to derive with respect to time, which means that we're going to have d something dt. That's deriving with respect to time. All right, now every variable is going to derive with respect to time, so each variable will be d variable dt. So in other words, if we're deriving a radius variable, that will produce dr dt by the chain rule, just as y produced dy dx through the chain rule when we did implicit differentiation. Volume would produce dv dt. Area would be dA dt, height would be dH dt. All right, every variable will, when it gets derived, will have a ddt attached to it. Okay, so let's take a look at that. If we look at example 29, we're talking about the spherical balloon I mentioned a moment ago, and we're looking at what's the relationship between the rate of change of the radius of the balloon and the volume of the balloon. So for starters, we need the volume formula for a sphere. Hopefully you remember that from geometry class. But if not, we can quickly look it up and see that volume is equal to 4/3 pi r cubed. So that's our opening geometric formula. Now what we're going to do is we're going to derive this with respect to time. Okay, there's two variables here, volume and radius. Right? 4/3 and pi, those are just coefficients. So they're going to be derived, but they're not variables. So we don't have to worry about doing the whole ddt to those things. Okay, so if we had volume, and we're going to derive volume, right? Well, this is like deriving x. What's the derivative of x? It's just 1. So the derivative of volume will also just be 1. All right, we don't have to write that, but it's technically there. The derivative of volume is 1. But because we're deriving volume with respect to time, it's not just 1, but 1 times dv dt. Okay, the derivative of volume with respect to time. When we do our implicit differentiation, we derive both sides of the equation. So afterwards, we now derive the right side. As I mentioned a moment ago, 4/3 and pi, those are coefficients, so they just slide right down into our derivative. And now it's time to derive r cubed. Right? Well, if it was x cubed, the derivative of x cubed would be 3x squared. So the derivative of r cubed will be 3r squared. Right? But again, we're deriving with respect to time. So not only do we have 3r squared, but we also need the dr dt because we just derived the radius with respect to time. So the chain rule says take care of the regular function and then derive the inner function. We're deriving the inner function, which is r, with respect to time, hence the dr dt. So this is our relationship right here. And this is a perfectly fine relationship. If we want to clean it up a little bit, we see that we have a 3 in the denominator, a 3 in the numerator. Those 3's can eliminate each other, and we can see that dv dt, the rate at which the volume is changing, is equal to the rate at which the radius is changing times 4 pi r squared. And there's our related rate for number 29. Okay, there's a connection now between the rate that the volume is changing and the rate that the radius is changing. There's a relationship between those, hence related rates. So if we try another one real quick, the conical tank in example 30. So a tank's being filled. It's shaped as a cone, so we need the volume of a cone. So volume is equal to 1/3 pi r squared h. And we're going to derive this just like we derived example 29. Okay, but this time we see r squared times h. That multiplication means that we have to use the product rule. So all of our rules are still valid, although really the only ones you're going to use are your power and your product rule. But they are still potentially there. So volume, once again, will derive to dv dt. And 1/3 and pi are coefficients. So they will slide right into our derivative. And now we have to derive r squared times h. So that's the product rule. Right, so here we go. Derivative of the first times the second. So r squared derives to 2r. And we keep the h all by itself. And then we just derived an r term, so we need a dr dt. All right, so that represents the fact that we just derived the radius with respect to time. Okay, and you can put this in any order. You could have 2r dr dt and then the h. You could have the h first and then 2r dr dt. It doesn't really matter because we're multiplying, so order doesn't matter. Okay. Now, product rule says derive the first, keep the second, plus now we derive the second, so that's dh dt, and keep the first, which is r squared. And again, we could write that as r squared dh dt. The order isn't important as far as the product is concerned. But now we have a relationship, a connection, all right, but we're relating some rates. What are they? The derivative of volume, the derivative of the radius, and the derivative of the height.